all the panelists who joined. Really great stuff. We've run slightly over, which is totally fine. Fascinating conversation. We obviously had a number of panelists on that one, so well marshaled. Imogen, thank you again. What that means is I think we'll just crack straight on into the next panel, and we won't go to a 5-minute break. But obviously, people are free to kind of jump in and jump out. But so our next panel session, we're going to be looking at aircraft integration as well. So we talked about some of those kind of core component technologies that deliver the propulsion, but how do we actually get them into aircraft, and what level can we scale up to? So I think we're just nearing readiness now for this panel. We're having a little bit of a challenge with our moderator, Dom. He seems to be struggling with his video screen, but Dom, I don't know if you can hear me at least. If we don't have him, hopefully we'll get him soon. No, we seem to be struggling with Dom. What I'll suggest is, oh, he's there. Brilliant.
I am here, even if my image is not. So I can only apologise for this technical difficulty.
It will be the kind of ghostly voice from the void.
Yeah, some would say a voice, a face for radio. So there we go. You're spared that.
Forced into a face radio. Okay, Dom, I'll hand over to you to introduce the panel session, and then our panelists as well. And then please go for it.
So there we go. Hello and welcome to the latest session at this year's ZeroAvia Hydrogen Summit. I am, believe it or not, Dominic Perry, Deputy Editor of Flight International magazine, and I'm your moderator for this topic, which is broadly titled Airframe Integration and Development, Delivering Zero-Emission Propulsion. So when we think about hydrogen-powered aircraft, what can spring to mind are the most futuristic-looking designs possible. For example, a blended wing-body aircraft with rear-mounted engines and no vertical tail. Well, such a configuration could be fully optimized for hydrogen propulsion. Any aircraft program is realistically decades away. The truth is that zero-emission propulsion will make its debut on much smaller aircraft that, in many cases, have been in production for decades already. However, although this offers a quicker route to market, will the conversion of existing platforms have enough of an impact to make a difference? During this session, we will attempt to explore whether retrofits make sense, what the impact might be, and the ultimate benefits of a clean sheet aircraft. So, without further ado, here are your fantastically well-informed panelists. We have Gabriele Teofili, Managing Director of ZeroAvia, and I apologise if I've mispronounced your name. Jacqueline Castle, Chief Technology Officer at the UK's Aerospace Technology Institute, and Phil Ansell, Director of the Centre for Sustainable Aviation at the University of Illinois. So, if each of you could take a turn setting the scene as to where we are and where we go from here. So, Gabriele, I don't know if you would want to kick off.
Yes, of course. Welcome everybody, and you pronounce almost perfectly my name. You know, we have so many different nationalities and culture in ZeroAvia. If you come to the hangar here, you will see so many flags hanging on the ceiling, and it's a demonstration that innovation is done in the UK, but it's done with a lot of people, a lot of culture from all over the world, like from me, from Italy. And yes, I think the topic is how to get to the entirety of aviation, and how to make small steps that were baby steps in the past, and we're demonstrating an initial capability, an initial potentiality to use hydrogen electric in aviation, and how to scale up. Retrofit is using existing airframes, entering into the airframes together with a collaboration with the airframe, the OEM, and then demonstrating that the integration is possible, the retrofit is possible, collecting the first flight hours is feasible, and once getting confidence, scaling up to the next generation of aircraft and to the next size of aircraft. ZeroAvia is doing this step by step, starting with a 600 kilowatt engine, which will be certified on the launching platform, which is the Cessna Caravan, together with Textron, and then approaching the next level, which is the 2 megawatt aircraft, and another level of number of passengers sitting in that aircraft. We strongly believe that because we are realistic, and we know that demonstrating that the engine works is not enough. Collecting flight hours will be the game changing in the revolution of the aviation, and we can do it only together with strong partners. only together with the whole ecosystem. And today, for example, there is the member of the government together with us in the representation of the ATI, for example. And here in the UK, we have made two incredible steps in the last 4 years, which is the first 2 flights with a commercial configuration of aircraft with the Piper and then with the Dornier this year. And we are looking forward to make the next steps.
So Jacqueline, as a representative of the government in some way, shape or form, how are you bringing the rest of the ecosystem along?
Yes, and thank you very much, ZeroAvia, for this invitation. It's a really great pleasure to be here tonight. So yeah, I'm Chief Technology Officer at the ATI. And just to explain then, so the ATI is an independent, not-for-profit organisation, but it's jointly funded by UK government and UK industry. So we define the UK's national aerospace technology strategy, and the latest is Destination Zero. And we advise government on funding projects that will enable, step changes, obviously, in aerospace technology to ensure continued growth of the UK aerospace sector and to ensure that we have a thriving and competitive industry. So I was just going to explain that Destination Zero has 3 roadmaps within it, the strategy. So it has an ultra-efficient aircraft technologies roadmap, a zero carbon emissions roadmap, and a cross-cutting enabling technologies roadmap. And the reason I sort of mention all these is that you might think that this summit would focus predominantly on the zero carbon technology roadmap. And many of the earlier panels have, of course, talked about hydrogen fuel cell systems and all of the sort of technologies that are specific to that part of the system. But the other 2 roadmaps are really also very important in the mission to enable hydrogen flight. So things such as the integration onto the aircraft itself has a great effect on what we normally and have been developing with aircraft for many, many years. Things like the hydrogen tanks are very heavy. So anything we can do with materials to get the weight down, how we actually integrate those into the aircraft, how we can make the aircraft as efficient as possible to sort of counteract some of the some of these weight increases that come from things like the tank are really, really important, and they come from other elements, if you like, of our Destination Zero strategy. So I'm sure we're going to come on in the panel to talk about a lot of those parts in more detail in a moment, but hopefully that sets the scene for what I can bring to this discussion.
So Phil, from an academic perspective, what can you bring to this?
Great question. So being an academic, we like to think about what's within the realm of the possible in the future. So for reference, I'm at the University of Illinois. I'm an associate professor of aerospace engineering, and I've been studying hydrogen electric aircraft since probably around 2018 is when I think we'd really kick off in earnest our efforts. I direct our Center for High Efficiency Electrical Technologies as well, where we've been studying hydrogen electric aircraft technologies under NASA support through University Leadership Initiative programs. And through that, we've been able to develop kind of some real key thoughts around what are key technologies that we need to integrate. You heard about some of those earlier. So things like superconducting power systems, cryogenic electric machines. But whenever we actually take these technologies and put them onto a future vision vehicle, how does that vehicle perform? How far can it fly? What's the energy required? How does it compare relative to incumbent aircraft? So we've been looking at a lot of that through our Cheetah program from an academic perspective that looks kind of further into the future of a clean sheet aircraft design. But in the meantime as well, we've also done some work related to retrofit aircraft as well. And we're kind of taking, that far future view and taking steps backwards. So maybe not going all the way to a turboprop replacement, but a regional jet. And what I can say is that, on hydrogen electric systems, if you take an Airbus A220-100 and you take the new 500 variant that's stretched, you can fit enough hydrogen on to carry about 100 passengers, 2,200 nautical miles. So we're really looking forward to kind of contributing in understanding what was within the realm of the possible as far as hydrogen electric systems are considered as integrated on aircraft. And with that, I guess what I will always say, and I always stress to people, is a hydrogen electric aircraft does not want to behave like most of our kerosene-powered aircraft systems of today. A lot of temptation is to say, well, I need to design an aircraft that has the exact same power capability, that has the same cruise altitude, that has everything looking and behaving exactly the same way as a gas turbine engine variant. And that's simply not true, because there are ways that fuel cells have really unique and specific benefits that we can point towards if we let the aircraft be designed by a fuel cell power system. And I would further kind of conclude by indicating that I'm really excited for what the clean sheet aircraft of the future look like. So Dominic, you mentioned blended wing body configurations. I think that a lot of people will say, well, long haul transport on hydrogen is impossible. And I would say, well, actually, I disagree. And in fact, a lot of the cases, the hydrogen electric variants will become better, or hydrogen, fuel tanks will become lighter in a proportional sense as we consider larger and larger variants that could be in a clean sheet design.
Okay, I suspect we'll come back to that topic later. I wonder, to kick things off, whether I could play devil's advocate for a moment and sort of advance the argument that against retrofits to start with. The sub-regional market is so small, the level of carbon emissions you're targeting from those aircraft is so small that the investment being poured into that is not going to make a difference. So why start small? Why not go for the bigger aircraft to start with and grab a bigger share of those carbon emissions?
I'm happy.
Go on, Jacqueline.
I was just going to say I'm happy to jump in there and say that, I mean, we're really pushing the boundaries of technology here in terms of bringing hydrogen onto civil aircraft. There's an awful lot to learn. It's not going to be possible to make that mountainous sort of step in one go and to leap straight into very larger aircraft. There's an awful lot of smaller steps to take to learn along the way, and proving out the technology, starting with smaller aircraft first, is the obvious way in my mind to make that progress, to at least start that progress off. I'm sure Gabriele will continue.
Yes, for sure. For me, it's important to underline that the technology available for the smaller aircraft. So this aircraft I have in the background, for example, 19-seater. This is the Dornier 228, which is flying this year, the whole year, with hydrogen electric engine. Just to repeat, hydrogen electric engine exists and flies in the UK. If you come to Canberra, you can see it with your eyes. This type of aircraft here have the possibility to be retrofitted with technology which is existing, and that I mention it with a terminology which is not very welcome by my team, which is boring, meaning there is a state of the art of a fuel cell, LTPM, for example, a simple technology for the gaseous hydrogen tanks and electric motor and inverter, which are available at least in ZeroAvia, but also in the whole electrical propulsion ecosystem of potential supplier, which allow us to issue a certification baseline and start a discussion with the civil aviation for a certification program, which is allowing companies like Airbus to back us, because they know that the certification basis is realistic. So I say boring because I want to have a configuration that is going to go through a certification program that can bring people on board, where people can sit and cannot think about the difference between a hydrogen electric and normal gas turbine in terms of safety and reliability. Again, I will repeat it for the third time, the boring configuration can't be used forever because there is a limit of power and function and performance and probably power to weight ratio, which can't allow to scale too much towards the bigger aircraft. The bigger aircraft require a different level of technology, which is, for example, another type of fuel cell, which we have under testing as well, which is HTPM, high temperature PEM, or the utilization of liquid hydrogen tanks, which may be used also for the 19-seater configuration, with a further retrofit and a further range extender in the future, once they receive a confirmation of the technological readiness level, which is good enough for certification. Those type of technologies require a level of confidence after testing, which we don't have yet. So jumping on the new technologies, which are lower technology readiness level too early, may mean not being able to fly demonstrator, not being able to fly engineering platforms, flying test aircraft, not being able to present a realistic certification basis to the authority, not being able to start the process to approaching that type of certification. So if we start with the bigger aircraft too early, we will probably fail because there will be not enough time, not enough money to complete the certification run. And from my point of view, what I tell again every single day to my team, let's collect the first flight hour of the history of hydrogen electric aviation with a certified engine. And the number of engine which can be used for retrofit for the CS-23 aircraft, for example, are big enough to cover that section of the business case. That business case alone does not cover the full story, because the idea here is not only to make profit with one side of aircraft, but is help the entirety of aviation to transition to green flight, is to help the entirety of the population to sit on an aircraft where everybody is not guilty of flying with producer of pollution. Is helping the whole aviation to change towards a cleaner future and to help the planet. So it's a step-by-step approach, with the first step with a realistic technology, and the next step with a visible realistic technology, and then the next step probably with something that has to be done starting from scratch.
And I couldn't agree more with Jacqueline and Gabriele on this. This is a big technology problem, and it's not just the fuel cells, right? It's also the electric power system. It's, you know, the thermal management systems that need to be developed and integrated and proven. And I guess I would further, you know, follow up with the example to say there's a reason why the 1903 Wright Flyer did not include 180 passengers, right, in its first flight. Is that, you know, whenever you're proving out new technologies, doing new developments, just the amount of risk and cost associated with getting to that, you know, big carrot that you want to get to eventually, it's just not tenable. It's not practical. I would also kind of take another angle at this to say that technology on the ground also in support and infrastructure is also not ready, right, for us to be able to have these massive amounts of energy be immediately ported to hydrogen. Indeed, the hydrogen revolution is coming, right? We see, you know, billions of dollars within the US through the hydrogen hubs being invested in the future hydrogen economy, which is wonderful. And aviation is coming alongside a lot of other sectors to advance hydrogen. But if we try to advance too quickly, we end up not having supply. And so as a consequence, let's develop, you know, our capabilities and prove out the technologies at these scales while the infrastructure, while the rest of the economy develops, such that, you know, the massive amounts of energy that are needed for civil aviation can be realized by hydrogen. I think that we as people don't realize how much energy aviation actually consumes. So, you know, we use roughly about 93 billion gallons of jet fuel every given year. And if you calculate the chemical energy contained within those hydrocarbon bonds, what you end up finding is that is equivalent to roughly about 14% of the electricity generated across the entire globe. That's a lot of energy. We can't just immediately flip a switch and assume that all of the hydrogen is going to be available for, you know, long haul 300, 400 passenger aircraft at the onset. But we'll get there, right? It's a process.
I think the message I'm getting is boring, and we should probably learn to walk before we run. I wondered whether there was also an element of societal acceptance from operating a small aircraft, getting people used to hydrogen as a fuel source. I don't know who would want to take that one.
I think I can start. There is a level of education. You're right, that is needed. So I make an example. We have, I don't know, probably hundreds of electric motors all around our houses, everywhere. Maybe not hundreds, but tens, many tens of electric motors around our houses. And when we started discussing about electrical propulsion some 10 years ago, 15 years ago, everybody was scared about the high voltage. But actually, it's a state-of-the-art development, which is achieved already for the last 150 years. And what is needed to be done for me is an education, is a demonstration, is bringing an electric motor in front of a combustion motor, and or a gas turbine as well, and showing the power of electromagnetism compared to the continuous explosion that is happening inside the combustion chamber. You know, the same works for the fuel cell. The fuel cell, they produce another magic, the magic of the chemical reaction between hydrogen and oxygen and production of electricity and water vapor. It's a chemical transformation of two elements in two other elements, and electromagnetism is just a force, which are a little bit invisible compared to a big explosion in a combustion chamber or the noise that you can get from a diesel or benzene engine, for example. We are so much used to have this noise under our nose in the cars, for example, and to know what's happening and to accept that some engine of the car can go on fire sometimes, because everybody has it, and you just leave the car and you understand. So I think the way to demonstrate that hydrogen electric works and how it works is to show it to people, to show how to identify and deal with the leakage of hydrogen from a tank, which is probably much easier in certain circumstances than the leakage of jet oil, which is going in the other direction compared to hydrogen, exactly inside the cabin, for example, if you get the leakage. I think there is a lot of wording about getting closer to reliability and safety and not too much education. I will just go in the square of the cities and bring electric motors, inverters, and hydrogen tanks, a small fuel cell, and to demonstrate how can you produce a small level of voltage probably for safety in this type of circumstances. But it's a technology which we have in operation already for many years, and it's much less dangerous and less noise, no noise actually, and technology that we use every day ourselves.
I would entirely agree. You know, being an educator as part of my job, right? I certainly have the hat oftentimes to say, yes, education is indeed something that will really help us to get across the finish line to overcome some misconceptions about hydrogen. But I also kind of see Gabriele's point about how this is just not something that people seem to interact with in their daily lives. So I often will like to take that consideration and say, how can we use then, you know, things that people do use in their everyday lives, or introduce hydrogen into people's everyday lives such that they can kind of start to understand, you know, what the inherent advantages, what the risks and other considerations around hydrogen systems are. And to provide an example of something that we did through our some of our outreach efforts. Actually, this was during the onset of COVID, whenever everything was closed down. We did an outreach program remotely where I actually got a bunch of educational fuel cell things. They're about this big, right, in size. They're these like single cell devices, and they were reversible. So we had some high school seniors within the local community that we actually provided these to, and they got to experience hands-on actually producing renewable hydrogen using solar power electrolysis. And you know, we're able to then build a hydrogen car, right, based off of some toolkits and components that we sent to them. So I think that efforts like this really start to actually make hydrogen fuel cells more boring. All right, to the point is that you kind of, once you realize that there's this box that is a fuel cell that you can touch and feel and handle, and you can produce hydrogen, right, and nothing bad happens, right? It removes a lot of the stigma. And the other side of that too is an example of a demo that I always want to do and never got around to doing. And that is that I've always wanted to take, you might remember the classic physics experiment or chemistry experiment where you take a hydrogen balloon and then the instructor kind of takes the match on a long pole and pops the balloon and everyone goes, it's, you know, the big shock. Have you ever done that with propane? The explosion's a lot bigger, right? And it's not a fair comparison, right? The amount of energy contained within a given volume of propane is a lot more than the same volume of hydrogen. But yet the example remains is that this is something, propane, that many people interact with within their daily or weekly or monthly, I don't know how often people get out their grills, right? Their lives. It's a regular thing. And so if you can kind of observe and understand based off of your experiences, right, how hydrogen fares and how it compares to other things that you can relate to, maybe that's one way that we can help to help people understand some of and get comfortable, right, with hydrogen use.
A quick question from the chat here is, what is the timeline for the hydrogen infrastructure full development? And I guess that one might be one more for you, Phil, than anyone else, although anyone else is clearly welcome to chip in.
Yeah. So what's the timescale of the hydrogen infrastructure?
Yeah.
Well, that is a question that if I could say with absolute certainty, with very low error bars, I would be probably incredibly wealthy. But instead, I'm making, my academic salary, which is fine. I get by. What I'm getting at, though, is that this is one of the big questions, right? The hydrogen economy has been hyped before. Why is it that this is any different? Because before we've seen it have a lot of interest and then kind of come and go. We saw this with hydrogen fuel cell cars, and battery passenger cars totally make sense from an electric perspective. I think that what's different now is the amount of support that is being poured in by many different governments, and I do think that the ball has started to roll, right? The snowball. And we're starting to see much greater adoption and support of hydrogen systems across a range of sectors. So if I was to toss my hat in, an appreciable amount of the proportional infrastructure would have hydrogen, I would say maybe starting by 2030, 2035, 2035, perhaps more so from, a more broad adoption perspective. And I see Jeff's comment in there, yes, as well. That's kind of what I was commenting on the hydrogen hubs. I don't think that the amount that's given to a single hub is commensurate or more than some government agencies get entirely, right? And I'm thinking that's showing some real serious horsepower behind developing what is needed for that future infrastructure. So that's my kind of dodge of an answer. I provided a time frame, but cut me some slack if I'm incorrect.
I shall ask you for the NFL results for the next couple of weeks.
It's difficult to give numbers, and what ZeroAvia does is to demonstrate that the infrastructure capability is possible to be developed. We do it ourselves. We produce our hydrogen here on site in Campbell, and we fly our hydrogen. That's not enough, of course. Now we will fly to other airports in the future in 2024, and we will need to bring our truck with hydrogen produced by our side. That's a little sad at the moment because the infrastructure is not ready, but it's also a demonstration that we need to follow the step-by-step approach we were mentioning in the beginning of the story. We can't believe that we make a revolution and everybody's following everything in advance without having any single object flying and demonstrating that there is a beginning of, I will not call it profit, but revenue. If we consider the ZA600, which can fit aircraft with 250 nautical miles or 300 nautical miles of range, we may need just 50 to 60 airports in the United States to be fed with a relatively small amount of hydrogen to allow this fleet of aircraft to fly back and forth. I think that's the approach that has to be done, and following the development of the engine, following the retrofit of the aircraft, following the operator, which are retrofitting this aircraft, following the routes, and then starting with this infrastructure. We have 100 people coming into the hangar here every single day, and there is a door in the hangar, and then 20 meters on the left is our electrolyzer, and it's our hydrogen storage tank. So it's not dangerous. It's just the reality, like we were telling before. It's a sort of education. The same can be done by the airport. The airport here in Campbell and wherever we will fly in the future is learning from us how to deal with hydrogen leakage, how to deal with high voltage production, what is the hazard that these two elements can produce, and how to mitigate the hazard. And actually, it's becoming state of the art. Sometimes we have the fire coverage here coming last minute and leaving exactly the moment when we switch off the hydrogen electric engine, because they got used. It's becoming the normality for them. We fly without being noticed anymore this year in 2023. And that's what is possible to be done. I don't believe it's all in one shot. That's why the step-by-step approach is the right one also for the infrastructure.
Okay. Yes, obviously starting with a small aircraft, 9 to 19 seaters, something like that. Is there a practical limit to the size of aircraft that can be retrofitted? And what governs that crossover point?
The key is range. So whenever I teach a class in sustainable aviation, and I always distill everything down to power and energy, right? And sustainability is really a large energy problem. Power roughly scales with weight and speed, and energy scales largely with distance and weight. Everything, of course, in aircraft scales with weight. But that's to say that, you know, the amount of hydrogen that you can physically fit within a conventional airframe from a retrofit perspective is going to be very much limited by, or the range is going to be the limit that you hit in terms of what retrofit potential you can actually practically reach. And so kind of whenever I highlighted, you know, the A220 example of, you know, we could fly 100 passengers around 2,200 nautical miles coarsely, right? From some rudimentary calculations and estimates we've made. That's kind of as far as I think we're comfortable as far as doing conventional fuselage extensions. You know, you could carve out more passenger, you know, cabin space and put more hydrogen on board perhaps. So 2,200 nautical miles is not a hard limit, right? But as far as retrofits are concerned, I think that you're not looking much farther than a couple thousand nautical miles max.
Okay. Do you want to come in on that, Jacqueline?
Yeah, I mean, all I was going to say was that, for example, you may need an A321 sized aircraft to replace the equivalent of an A320, for example. So certainly at the moment with the technology anticipation of sort of development that we might be talking about at the moment with the knowledge that we have today, then there's certainly a limit on range compared to, you know, the larger aircraft that we have at the moment available. But of course, then we need to take these small steps, see how things evolve, look at the efficiencies that we can gain on airframe or on other materials to try to counteract some of the sort of increase that comes from the need to carry the hydrogen in a different way to the way that we've carried kerosene all these years, you know, to do that sort of trade-off. But there will be a limit to start with, no doubt about that, and a limit to sort of the retrofit side of it as well, because the aircraft, you know, obviously are not, you know, manufactured in conjunction with the system itself. So you'll lose some efficiencies in that sense as well.
Yeah, I think completing the answer, range, of course. I mean, the variable are those, no, payload and range and weight is the same. There is a variable which has to be considered, which is the level of acceptance of penalties from the operators and from the population that needs to accept the entry into service of a new technology. So if I manage to certify an engine and to fly with the Cessna Caravan and a full hydrogen electric engine, it will be no pollution, at least between A and B. So not in the production of hydrogen in the beginning, of course, but there will be no pollution. It's an advantage. It's exactly what we want to do in order to achieve a decarbonization goal. Demanding to have absolutely the same profit and performance at the very beginning, at the very first flight hours, is a high demand. I know that in order to be certified, I will need to be conservative in the beginning. And then from the conservativity of the first configuration, I will need to optimize and to reduce the weight and to extend the range. We were doubtful about the acceptance of this initial partial penalty in payload. Instead, we found customers and operators which are telling, I want to do my part.